When our little girl was born, we got a Subaru. It's where she said her first word,
No.
saw her first day of school,
Bye-bye.
made a best friend forever.
Oh my God.
The back seat of my Subaru is where she grew up.
What?
The 2015 Subaru Forester.
What?
Built to be there for your family. Love, it's what makes a Subaru a Subaru.
University Subaru.
The wise choice! Good morning and welcome to Radio Friends on this Wednesday, March the 4th. We have a very interesting guest with us today. Jack Schultz, Life Science Center.
Good morning.
Good to have you here, Jack.
Great to be here.
You came in today and said, well, we're going to talk about
Epigenetics.
epigenetics.
Yeah, epi means above, sort of, okay, and that means that there's a kind of a higher level of organization to your genes. You know, you and I don't look a lot alike. I'm sorry. I don't know which of us is sorrier.
Okay.
Despite the fact that we have, well over 99.9% the same genes.
Each person has
Yeah.
99 and 9/10%
Right.
the same genes
At least,
in
right.
them.
That's right. Mhm.
But it's that fraction of a percent.
There are two things. The fraction of a percent does make a difference. But the bigger difference is this. Genes only do what they do when they're turned on. And they're not all on all the time. Like right now, the genes for producing hair on top of my head are not functioning. They've been turned off, right? And some genes get turned off as you age.
If you could turn those genes back on again,
Yeah.
would your hair start growing?
Yeah, if I could do that, sure. Yeah.
Well, someday, I'm sure someday.
Well, think about this. There are a lot of genetic-based diseases, and if we could figure out how to turn those genes on or off, depending on whether how they're causing that, yeah, that'd be great. Usually when you turn genes on or off, every gene is like a stretch of DNA, in your cell, and it's got two parts. One is has the information for making something, usually a protein, like hair protein. Okay, the other part is like a trigger. It turns that gene on and off. And it does that under certain circumstances. Some of them are on all the time. Others are only on when you need them, when the environment calls for it. A lot of them are turned on and off by your hormones. Hormones are a big signaler when it comes to genes. But the way you look and are, the way I look and behave and everything, has more to do with which of our genes are actually turned on and functioning now, or turned off, than it does what genes we actually have.
Okay.
All right. So, since it's important to be able to turn those genes on and off, our bodies have a whole system of regulation to make it easier or harder to turn those genes on and off. Because you don't necessarily want some of them on all the time, and you don't want some of them off all the time. So there's an access problem. The genes are on the DNA. They're wrapped up really tightly inside a cell, and you need to get a signal to them to get them to do what they're supposed to do.
As I sit here listening to you, you realize what a miracle our body is.
Oh.
What an absolute miracle the human body is.
Here's a science cocktail party thing for you, okay? The amount of DNA in every one of your cells, which we can't even see, right? The amount of DNA in there is over 2 meters, almost 7 feet of DNA strand in every one of your cells.
In every cell?
In every cell.
How is it all crammed in our body?
Well, it's wrapped around little spools. Wrapped around spools. If you put your earphone cord in your pocket, it's always tangled, right?
Right.
That's because there are way more ways to be tangled than to be what you want. All right. How do you solve that problem? You wrap it around a spool of some kind. In fact, they sell lots of gadgets like this to keep it organized. Well, your DNA is organized the same way. But because it's wrapped up so tight, signals can't get to the genes to turn them on. So there has to be a mechanism for opening them up, releasing them from the spool so that signals can turn them on or off, and then wrap them up again. It turns out that process can be passed on to offspring, so that if you opened it up and turned a gene on, keeping that open can be passed on to offspring. So if this were a response to, say, a chemical in your environment. In fact, this is really, Dr. Rosenfeld in the Life Sciences Center works on this. She finds that exposing animals to BPA in plastic bottles, that kind of thing, it's just mostly gone from plastic bottles now. If you expose mom mouse to this, the genes in her body are changed. Their expression is changed, not what they are, but how they work is changed, and that's passed on to her offspring, and has really interesting consequences.
So what you're saying basically is what your mother or father did even before they were bearing you, before mom was carrying you in her body.
That's right.
Has an effect on what you are today.
That's right.
And the way you act today.
That's right. In fact, it's really difficult to understand where various psychiatric disorders come from. There always seems to be sort of a genetic component because it looks like it's traveling in the family, but a lot of times that's hard to see. And a lot of researchers are now guessing that parents exposed to something, maybe a disease, maybe an environmental problem of some sort, have their expression of their genes changed, and that's passed on.
What about stress? What if a parent is exposed to stress before she became pregnant?
Right.
Can that be carried on to the child, and then that child carried on to the next child?
Yeah, that's very true, but let's not blame mom entirely. Although it's really easy to do that because, mom's the main one here. But it turns out male parents as well as female parents pass on anxiety to offspring if they are made anxious during their lives. And here, a classical experiment is you frighten a mouse by giving it a little shock, and you associate that frightening experience with a smell. Okay, and eventually the mouse learns not to go where the shock is. Okay, that's easy. Turns out, so do its offspring, even though they never experienced that smell before.
They
never
but they
experienced
know that was carried through to them.
That's right.
They know that they associate that smell with something bad.
That's right. Mm-hmm.
And they don't go near it.
So this is a whole revolutionary new way of looking at inheritance. Classical ways of looking at inheritance mean that you have to wait for genes to actually change what they are. Fundamental changes in their structure before you start to see changes in subsequent generations. With this mechanism, you can get changes in what genes are doing in one generation and pass that change on right away.
We're almost out of time, Jack, but how long have you known this? How long has this been?
This body of information is well under 10 years old.
So it's fairly new.
And the real big breakthroughs have only come in the last couple of years.
Okay.
So they're real new, yeah.
A lot going on at the Life Science Center.
We'll be having a symposium conference on this.
Oh, next Friday,
Next
right?
Friday, March 13th and the 14th and 15th. Watch
where?
for it at the Bond Life Sciences Center.
Okay. So, and it's open to the public?
Open to the public.
What time?
All day on Saturday the 14th. Probably Friday evening as well.
It'll start Friday evening.
And run all day Saturday.
And all day Saturday. Mm-hmm. It's open. It's free to the public at Bond Life Science Center, MU campus.
That's right.
All right, Jack Schultz, thank you so much for coming by.
It was a pleasure, as always.
Please come back again.
Great talking.
I can sit and listen to you forever.
You're right.
Tomorrow, Second Chance in the JC Art Club. Our program directed by Travis McMillen, Reynolds Journalism Institute. Audio is Pat Akers from KBIA. Our floor director is Brendan McDermott, and our assistant producer and guest coordinator, Uncle James Mauser. Drop me an email if there's something you'd like to hear or see. Bye-bye.